Welcome back! We're looking at several common types of data structures, and in the previous video, we covered array-based structures. This video will cover linked data structures. We will look first at linked lists, and then at linked trees. With arrays, values are stored directly next to each other in memory. In linked data structures, values can be anywhere in memory, but each value is linked via a pointer to the next value, forming a chain. Following the chain is somewhat like a treasure hunt game, where each stop provides a clue for where to go next. This linked chain provides an alternative way to implement a list data type. This is called a linked list data structure. In this example, we have a list of 4 characters, L-I-S-T. Let's have a closer look. Each location along the chain is an object called a node. Each node consists of 2 variables, one for the stored value, for example the letter L, and the other variable for a pointer to the next node. We must also keep track of where the whole chain starts. We use the term head to refer to the first node. Some linked lists also store a reference to the last node, which is called the tail. The last node has a null value for its pointer, since there is no node after it. Modifying a linked list is easy. To remove the S node, all we have to do is repoint the I node to the T node. The S node is now no longer part of the chain. We're left with LIT. To add a new element anywhere in the list, create a new node and repoint the surrounding links to include it in the chain. Our list is now LINT. Adding to the beginning is equally simple. Create a new node, point it to the old head, and make it the new head. Our list is now FLINT. As you can see, linked lists are very flexible, and unlike arrays, there's no fixed length. Just keep adding nodes and linking them. But what are the drawbacks? One thing that arrays excel at is being able to access any item in the array directly. But with linked lists, the only way to get to, say, the third item is to start at the head and loop through the chain one by one until you count off to the third item. For a long list, this could be a lot of looping. Let's review the pros and cons of array and linked lists. I'll show some scenarios. For each scenario, identify whether an array list or a linked list implementation would be more efficient. Feel free to pause the video if you want more time. Which is more efficient for inserting at the beginning, an array list or a linked list? A linked list will tend to be more efficient because, with an array, all the values in the list will need to be shifted over to make space for the new first item. But inserting into a linked list is just repointing a couple links. Which is more efficient for accessing an element by index? An array list is more efficient in this case because arrays allow instant access to any index. With a linked list, you will have to loop through and follow the chain to that node. Which is more efficient for inserting at the end? Actually, that's sort of a trick question. They're usually both efficient. Adding to a linked list is always trivial. And for an array list, if the array still has empty spaces left, it's trivial to fill one in. The only hitch is, when the array is full, you need to copy over to a new larger array before you can add to it. We don't expect you to memorize the pros and cons of linked versus array lists. The point of this activity is to start to think critically about how different data structures each have their strengths and limitations. To recap, a linked list data structure uses a chain of nodes that each holds a value and then points to the next node in the chain. The first node is called the head, and the last node is the tail. If you're programming in C# or Java, you can make use of the built-in linked list class. Before we close out this video, I'd like to talk about one more thing. Linked data structures can go beyond lists. They can also be used to construct trees and graphs. Take our linked list node, and instead of just one pointer to the next node, give it multiple pointers to multiple child nodes. Now we have a linked tree. This kind of tree is built into the JavaScript DOM libraries in the node class. In JavaScript, each node represents an element in the HTML document, and it has a property called child nodes. That is a list of other node objects that are children of the element in the tree. The same linking scheme we used for a tree can also be used to create a graph. Just point the links wherever nodes need to be connected. To recap, linked data structures consist of nodes that each link to other nodes in the structure. They are very flexible and can be used to implement lists, trees, graphs, stacks, and queues. One downside of linked data structures is that it can be difficult to jump directly to a point in the middle. You often need to start at one node and follow the chain. In the next video, we will look at a type of data structure that is optimized for getting directly to a specific value, data structures that use hashing.